because it's awesome. It's time for some more Styropyro. Specifically, the 20,000 watt microwave oven, or the MACROWAVE. And did he yoink a transformer from a pole? What? For those of you who don't know me, I'm Tyler Fultz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Look how happy he is. It's good to see him doing well.
Hear me out. A typical microwave oven is about 1,000 watts. Well, I'm wondering what kind of fun could be had with an oven that's 20 times stronger.
Yeah. He's gonna make plasma, isn't he?
Now, I'm sure many of you have wondered this as well. But if not, there are a few things that a 20,000 watt microwave would accomplish. Now, the obvious one is cooking food faster. I mean, in this day and age, I shouldn't have to wait minutes to cook a Hot Pocket. Oh no, this should take seconds.
The question is with Hot Pockets, though, is it still going to be boiling lava hot on the outside and ice cold at the center? You might need 20,000 watts to pull that off.
Microwave experiments should be 20 times more exciting as well. I mean,
it's already on fire.
Even an oven like this is capable of some cool tricks. So I'm hoping that throwing obscene powers at these classic demos will give some fun surprises.
I love that he's got it set up right next to the flammable container. I don't know if there's anything actually in that, but when you see lockers and cabinets like this at a nuclear power plant, there's separation requirements from anything else that can combust. So probably wouldn't set your microwave up right next to it. And I also see another cabinet adjacent to it that also has the same flammable hazard. So yeah. But for all I know, it's safe and those cabinets are completely empty. Clearly just making fun of safety people, I'm sure.
And this brings up my last point. The plasmas that could be made would be hellish. Like seriously, if you thought plasmas in a normal oven were cool, imagine the kind of witchcraft that you could pull off at extreme power.
Some fusion reactor designs, like tokamaks or stellarators, use microwave heating to heat the plasma hot enough to cause nuclear fusion. Technical term is electron cyclotron resonance heating, or ECRH, but it's basically the equivalent of sticking your plasma in a giant microwave. What it does is it just energizes those electrons to raise its temperature high enough to achieve nuclear fusion, which is not unlike how a microwave cooks your food.
Is there anything that it wouldn't melt? There's only one way to find out. So, how do you get 20,000 watts out of a microwave
Put a bunch of microwaves together.
Well, you only need to upgrade 2 components. Let me open one of these up and show you what I mean. Now, I gotta say it, the power supply in a microwave oven is lethal. In fact, when science hobbyists get killed by their projects, more often than not, it's because they were screwing around with microwave parts like these.
I've missed you, Styropyro. And yes, I've heard him mention this in a lot of his previous videos too, about how dangerous microwave ovens can be if you don't treat the components with the amount of respect and safety precautions that they need. Though he's done stuff like this with microwaves before, so I'm not really worried about him. I mean, it's just like any other hazard. People are afraid of radiation, for instance, but you just need to put the appropriate protective measures in place for the job, just like anything else.
Anyway, this right here is what generates the microwave radiation in an oven. It's called a magnetron. Now, interestingly, this is actually a vacuum tube, which means unlike phones, TVs, and radios, the main technology in microwaves is the same as it was 70 years ago. Pretty cool, right? So can you just dump more?
Same thing is true in nuclear power plants. The nuclear power plant that I worked at was built in the 90s, but designed in the 70s. So I guess a bit younger than this microwave technology. But we still had old school plasma screens that looked like this.
Power into this magnetron and get more power out? Well, you can, but only to a point. I've actually tried this, but I only got to a few thousand watts before it blew up. So this method won't get me to 20 kilowatts. I simply need a bigger magnetron. Now, unfortunately, even though oven magnetrons are a dime a dozen, big ones are really hard to come by. In fact, I've been waiting for years to make a video like this, but I simply couldn't find a big magnetron. However, my luck finally changed. Enter the Megatron. This water-cooled beast is rated for 16,000 watts of drive power, and I plan on pushing it to 20. It's actually
Yeah, I can understand the need for water cooling at that point, since water's a way more effective heat transfer medium and coolant than air, at the cost of adding a water cooling system and a lot of added weight.
kind of funny that I'm even allowed to own this. Now there's a bit of lore to how I obtained this beast.
He always gets his hand on the craziest stuff.
It was an eBay purchase, but it was not me that found the listing. It was the notorious Discord entity Charizard Wrecked that tipped me off to some monster magnetrons being sold as heat exchangers. I bought a few, and although one came DOA, 2 were still functional. I was salty about the dead unit, but then a scorpion jumped out of the package, which I thought was a pretty cool consolation prize.
What? Okay. I did not expect to see scorpions when I clicked on this video.
Anyway, what do I do with this now? So can I just jam this thing in there and call it a day?
Is he going to put the scorpion in the microwave? I don't know if he'll do that.
Well, there's one problem with that. It don't fit. I could have just built a bigger waveguide, but I thought back to some of the oldest microwaves that I took apart.
This looks ancient.
And I remembered that some of the oldest ones had big waveguides inside of them. So I picked up this old radar range microwave from the 70s, and I just love how it looks. But to be honest, it's also just built like a tank. Like, they don't make microwaves like they used to. Gosh, this thing weighs like 80 or 90 pounds.
I was going to say, it looks super heavy. They got like lead in there or something.
It's a real beast. The huge magnetron fits perfectly inside the oven, but it brings up another issue. How am I going to power it? I need 20 times more power than this thing can provide. So perhaps I can take apart 20 microwaves, chain together the transformers, and power it that way? Nope, that sounds horrible. I have a better solution
I'm glad you didn't do that.
in mind. I bought this cute distribution transformer that'll be perfect for the job.
Okay, if that's little to him, then what's a big one? The main output transformer from a nuclear power plant? Probably.
Now it is technically a bit undersized for the load, but for short runs, it'll be fine. Alright, it's all wired up now. Let's fire this beast up.
Wow, I think this could be getting up there with the Soviet military tech video. If you haven't seen my thoughts on that, please check that one out.
Now before I stick anything crazy in there, I just want to try boiling some water to make sure it actually works.
Sure.
Now I will admit that running this thing isn't quite as straightforward as running a household oven, so let me show you the startup sequence. Now,
Here we go.
You do have to close the door because there's no safety interlock to prevent you from cooking the room if you leave it open.
Of course there isn't. Also, it looked like it didn't quite close all the way.
So I'm going to start by firing up this water pump here. So next,
Sure, it is
I'm going to
water
go here
cooled.
and fire up the magnetron filament. Next, I'm going to hit this switch here, which energizes that boosting auto transformer, which then feeds my variac. And now, I'm going to take my variac and crank it all the way to 100.
Love these old school giant dials you see. You don't really see those anymore.
And this switch right here is what finally powers it up.
Pillbox,
So,
danger, you
let's
will
boil
die.
some water. A typical microwave oven takes nearly 2 minutes to bring a cup of water to its boiling point.
Okay.
This one goes beyond that in seconds. Yes, water
Not gonna be much
actually
water left.
explodes because it superheats faster than it can boil.
That's a real thing. Superheating is when you go way beyond the boiling temperature of 100 Celsius. So the reason why this happens in a microwave is microwaves heat uniformly. And there's no nucleation points or points where bubbles form. So you're not going to see this on your stove because that heats from the bottom. And especially a microwave like this that heats it up so quickly, and if it doesn't form bubbles, then yes, any disturbance to that superheated water will cause it to flash to steam like that. It's the same reason why there's a lot of operating parameters in nuclear power plants to avoid hydraulic transients, such as slow controlled opening of valves for a heat exchanger, and why you fill and vent them.
If water explodes in there, imagine what'll happen to things you aren't supposed to microwave. I'm sure you're dying to see how fast food will cook in that thing, but the fact that it makes water explode means I gotta try some of the classic microwave experiments first.
Oh, of course.
So, let's see what it does to a light bulb. What could possibly
Like they mentioned food, and now we're going to light bulbs.
go wrong? All right,
I'm glad he's at a safe distance.
here we go.
Yeah.
Wow.
Would you expect anything less than that?
It's just instantaneous.
Mm-hmm.
Oh my gosh. Oh, that's hilarious. Look at that. It just turned it into dust.
Wow.
Oh, that is so funny. Jeez. By comparison, when I tried this in a normal oven, it took nearly 10 seconds to melt through, and it didn't even come close to exploding. Is it a good idea to microwave an egg?
Well, 20 times more powerful. I mean, yeah.
Let's find out. All right, here we go. Oh my goodness. I tried an egg in a normal oven as well, and it took over 30 seconds to pop and wasn't nearly as violent. I'm curious what'll happen to a plasma globe inside this thing.
Oh, let's see.
All right. How do I even do this kind of stuff?
Because it's awesome. Slightly longer than the light bulb. Oh, that's so cool.
That was so loud. Oh my
I mean, as I said earlier, microwave heating of plasma, it's a thing.
gosh. Wow. That was crazy. Oh yeah. Oh my goodness. It's just
a
like
pedestal.
powder. Oh, you gotta see this. That was reduced into dust. Into just dust. There's like, those pieces are so tiny.
Wow.
That's crazy. That actually exploded so violently that bits of glass shot holes in the microwave guide cover. Yikes.
Whoa.
Now speaking of plasma, the metallic
Yeah, a lot more energy in that system. I'm glad he's at a safe distance from this thing.
coating on this chip bag should be pretty interesting. Let's activate the shrink ray.
Wow. How fast it is, though.
Instantly.
Because he's right. You've seen like these classic microwave experiments where it just takes a while and you're just on the edge of anticipation. I mean, I've seen videos of this since YouTube first became a thing, but it's just so much faster.
That candle can be crazy in a normal oven, so I figured it'd be worth trying in this thing as well.
In a beaker.
A funny side effect of all that plasma is that it turns the air in there into deadly nitrogen dioxide gas.
Yeah, I guess you could, theoretically, and I'm just gonna throw that out there. A 20,000 watt microwave isn't a typical nuclear waste management tool, but you could use microwave heating to do chemical processes such as that to break down hazardous waste and certain types of radioactive waste, the goal being just a smaller overall volume and making it easier to manage. It could work in tandem with a vitrification system, essentially converting waste into a more stable glass-like form. Or just even having the microwave burn away radioactive organics. Though any of this stuff, this setup, I couldn't imagine putting it into a super controlled, radiological controlled environment where every isotope would need to be accounted for. Imagine a radiation protection technician doing a survey in the crushed light bulb and plasma bulb ash and dust that you would see in an experiment like this. But it's an interesting thing to think about, I guess.
Which gives it that brown color. Now, if you're wondering how I'm filming inside the oven, I just have a hole drilled in the cavity there. And then, over here, I just have a cell phone that's just taped to the walls there. Now this works
the same way
because
Nile Red did it.
the hole is pretty small relative to the microwave wavelength, so it doesn't let much radiation out. Now, I'm not the first YouTuber to use this technique. I think Cody's Lab was the first to do it on YouTube.
Oh, sure.
But then Nile Red has a good video on microwave plasmas that uses this, and then Steve Mold actually has a whole video about, filming inside a microwave. Anyway, I think it's time we cook some actual food in this thing.
Here we go.
And it's funny because after years of doing everything with a microwave that you're not supposed to, I'm finally going to come full circle and use a microwave oven to simply heat some food.
I still wonder if the Hot Pocket's going to somehow still be ice cold in the middle. I mean, you would think no, because 20,000 watt super microwave, but that's just something I've always seemed to run into with Hot Pockets.
Let's start with a Hot Pocket. The instructions say it needs to cook for nearly 3 minutes in a puny home oven. I'm hoping this MACROWAVE
It doesn't have instructions for 20,000 watt microwave? Come on.
will cook it faster. Well, it didn't explode, but I'm not sure if that's a good thing or a bad thing.
Hot Pocket lava? All that.
Alright, let's take a look. Oh yeah.
Shrinking radioactive organics. I know Hot Pockets aren't actually radioactive. It just seems like they are.
Looks done. Oh yeah, it feels done too. Well, there's your 10-second Hot Pocket.
201?
Now the most surprising part about this is that it cooked evenly, because I know this oven has some hot
Thank you. That's the thing about Hot Pockets. They're hard to cook evenly.
spots. I wonder how quickly a hot dog will cook in this thing.
Is he gonna eat it? Is he gonna eat the Hot Pocket? Oh, there it goes.
I was kinda hoping it would explode, but at least it was cooked in seconds.
I'm kind of surprised it didn't, actually, because I've inadvertently exploded hot dogs in a regular microwave. I usually just cut some slits in it to avoid that.
She left it in there way too long, judging by what it looks like afterwards. I chucked a potato in there without stabbing any holes in
Okay.
it, also with the hope that it would explode. But unfortunately, it simply flash cooked like it was supposed to. It did make some funny whistling sounds, though.
That's a nice side effect about this one, is maybe it's less prone. Maybe the added heat and the added uniformity just makes it less likely to explode, in the case of food items anyway.
In fact, a lot of foods make that funny whistle, and pickles turned out to be one of the best noisemakers.
Whoa.
Let's test another microwave food classic,
Hit
popcorn.
the popcorn button.
This one was actually kind of disappointing, because it took 30 seconds to pop fully. Now this is several times faster than a normal oven, but I was hoping it'd be instantaneous. At least it didn't burn though.
Wow.
Now it's time for everybody's favorite food to microwave, the grape.
Uh,
And you know what? Let me go ahead and cut it almost in half, just to make sure, it heats
Grape
nice and
plasma.
evenly, Like this. And yeet.
Looks like the grape just gave up the ghost there. It's kind of funny.
Unfortunately, the fragrant smell of roasted grape is hidden by the suffocating nitrogen dioxide fumes, which is the deadly brown gas left in the beaker there. Instead of cutting a grape in half, I just tossed in some unmodified grapes to see if I get the same result.
Just more of the gas.
Yep, grapes are haunted. These grape plasmas are incredibly bright, but of particular interest is their color. They glow white and even have bits of blue coming through. I'm wondering if they're being heated beyond white hot to blue hot. The big brain way to answer this question would be to take a UV visible spectrum, fit it to the Planck radiation law, and determine the temperature that way.
I mean, yeah, that's the exact way to do it, but what's he gonna do?
But you know what? That doesn't sound nearly as fun as chucking a bunch of metal in there and seeing what kind of hell is unleashed. So yeah, let's do that.
Sparks
Let's see if
and
the
plasma.
microwave can melt magnesium ribbon, or at least see what kind of plasma it'll make.
The thing is, you could theoretically use something like this to accelerate particles in linear accelerators as well. Just need maybe a slightly different layout.
Not only did it melt and burn in there, but it also managed to show off some of its green spectral colors,
that's cool.
which is in contrast to the white you get by simply burning it in air. Aluminum melts at only slightly higher temperatures than magnesium, but for the sake of curiosity, I'm going to toss some foil in there
Classic,
anyway.
don't put tinfoil in the
Alright,
microwave.
here goes nothing.
Because this happens.
Now that is like an arc furnace. Oh my goodness. Now it's time for something more challenging. Copper needs to be very hot before it melts.
way hotter.
So let's see how it holds up in the macrowave.
Okay.
Oh yeah, it melted almost instantly.
Using that net structure, I mean, gave it a lot of surfaces to absorb all of that microwave energy, and it's so thin, so not surprised it didn't last as long as the bag of popcorn for sure.
Now this also brings up an important point about the glass. It's actually astonishing how well these Pyrex beakers have held up to the plasma. The same cannot be said about this Pyrex bakeware. The difference is that the beakers are made from borosilicate glass, which has very low thermal expansion. Pyrex bakeware used to be made from this as well, but has since been changed to tempered float glass, and its internal stress patterns are easy to see in a polariscope.
Sure.
This change is unfortunate for home.
I know tempered glass is more vulnerable in general when exposed to extreme temperature differences, especially along the edges, so figured this wouldn't hold up as good.
Science, but it does make for less dangerous breaks in the kitchen, as it tends to explode into tiny bits as opposed to razor shards.
True.
Anyway, let's move up the temperature scale to some thermite. Thermite is so hard to ignite that you can buy it pre-mixed and have it shipped to you without crazy restrictions. I'm hoping this macrowave can achieve its high ignition point. Yeet!
It does ignite though. Burning glass.
So that's what it took to break one of those beakers. It basically just exploded in there. All the iron product is dispersed in little droplets. That was fun. Although that reaction made molten iron, it was kind of cheating due to all the chemical energy
Okay, glad he's wearing a mask on that.
released. Let's try directly melting some iron in the form of steel wool.
Sparks. No?
Yep,
Melting fun.
no problem there. Next on the list is titanium. This stuff is quite hard to melt, but I think the microwave can pull it off. Alright, let's melt some titanium.
Sure. One thing is, he's using a lot of stuff that's fairly thin. It has a very high surface area cross-section, so a lot of that energy can be translated to melting, as opposed to a brick of titanium, which might be a bit more challenging. Not to say it wouldn't melt, but it probably wouldn't melt as fast.
Man, I'm gonna see spots for a long time. That was so bright. Oh my goodness. Oh my.
It's still going.
I'm running out of metals with higher melting points, so this time I'm going to try making rubies, based on a cool video by Nighthawk and Light.
Cool.
Okay, so I ran into a lot of issues with this one, but it was mostly due to stupidity on my part. The gist of this procedure is that you use a microwave plasma to melt an alumina-chromium mix, which yields ruby. However, for some reason, I thought Ben's procedure generated the alumina via an exotic thermite reaction between chromia and metallic aluminum. This false assumption led to a lot of broken glass and several failed shots. The funny part is that my
much
chromia
glass did it go through?
thermite still ignited with ease,
Probably a lot.
which is probably even harder to pull off than making ruby. However, when I used alumina like I was supposed to, I still ran into issues. the plasma escaped and the glass container exploded after just a couple seconds. Fortunately, this was still enough time to finally make some ruby. Thank goodness. You know, the fact that this can be done in a normal oven means I really haven't hit an impressive temperature yet. So, let's cut the fluff and move to something extreme. It's time for the metal with the highest melting point, tungsten.
Wow, okay.
The melting point of this is literally thousands of degrees above anything else I've tried so far, so this one might be challenging.
Tungsten's high melting point and high density makes it not just resistant to heat, but also radiation exposure, ionizing radiation. So it could be used as a plasma-facing material in a fusion reactor where it's constantly exposed to high levels of heat and radiation. It would also make really good radiation shielding, even better than lead, though more expensive. Though there could be situations where you just don't have the space, like in a medical application where you want shielding, that you're better off investing in the more heavy tungsten compared to lead just because you don't have a lot of space to put the lead in there.
Alright.
Sound.
For whatever reason, the plasma in this beaker kept escaping confinement, so I couldn't give it a long enough zap.
Something you never want to hear when operating a nuclear fusion reactor.
The wire may have burned a bit in there, but there wasn't any clear indication of melting, so I decided to give it another go on ceramic fiber. Heck. Oops. Waveguide flashover. It turns out, free plasma in the oven is really bad, because it jumps back to the magnetron through the waveguide. I used these micro waveguide covers, which buy about a half a second of plasma escapes, but this one got all crispy without me realizing it. It won't take many flashovers like this to destroy the oven.
Yeah.
And unfortunately, this is not the first time this has happened either. Alright, here we go. Oh, heck. Alright, we got a new waveguide cover.
Edited heck.
Let's try this again.
That was so cool. There goes a chunk.
That run clearly melted some of the tungsten, as you can see by the beading on the wire.
Sure.
How that is impressive.
Yep.
So this macrowave is capable of melting any metal. But the thing is, I'd bet that plasma in there is substantially hotter than even tungsten's melting point. Unfortunately, there's nothing tougher that I can melt, so I can only say it's at least 3,422 degrees C.
I like this scale of telling how hot something is just by seeing what it can melt. So I guess it's your way of saying off-scale high in terms of metal meltability. Sure.
Now, something that I found is that although tungsten is the toughest metal I can throw in there, it's far from the most interesting. So to get to the point, what happens if I microwave a lithium battery? Well,
Ultimate
embarrassingly,
lithium.
I couldn't get one to pop. The oven itself would flash over before anything happened to the battery. I tried cheating by using some steel wool to initiate a plasma, but even then, the plasma refused to stay contained. So, I decided on a different approach. I carefully opened one up and extracted the lithium foil inside. Microwaving this foil gave a surprising result.
Macrowaving. That's some fun color.
That incredible red coloring is due to lithium's atomic emission spectrum. What I expected to see was maybe a few red flashes in an otherwise white plasma, simply because the temperatures are so high. The fact that the colorful spectral lines were favored opens up the possibility of all sorts of colorful plasmas.
Oh, that's great.
Now this brings up the question, what happens if I start chucking a bunch of weird chemicals and metals in there? Can I make a full rainbow of plasmas, at least to a Roy G. Biv approximation?
I'm wondering if you can do it all at once. I'm not sure. It would take a careful placement, I'm assuming.
Well, there's only one way to find out. For the next weird metal, let's try a lump of calcium. This sample is surprisingly still shiny, even though I've had it for years. I'm hoping it'll show off its orange spectral lines when yeeted into a plasma.
Yeeting it. Looks pretty orange to me.
Well, that was easy, and stupidly bright as well. On to the next one. For yellow, I'm gonna zap some sodium metal.
Ooh, okay.
For reasons I'll get into soon, zapping the angry and highly reactive metallic form is a
Super
totally
reactive.
unnecessary way to see the sodium spectral colors. However, for the sake of memes,
I was gonna say, since when has Styropyro done anything that's necessary?
I'm gonna do it anyway. I do need to address something first though. The last time I pulled out this lump of sodium, so many of you freaked out over the quantity. Now let me tell you a little something. This little chunk right here is nothing. In fact, when I was 13 years old, I obtained 2 400-pound barrels of metallic sodium. Now that's a story for a different
Feel compelled to ask why, but maybe I just don't want to know.
day. But be assured, this ain't much. Well, anyway.
Context, right?
Yeet.
I wonder if I could convince the Nuclear Regulatory Commission to use the term yeet when starting up any type of reactor, whether it be a fission or a fusion reactor. It's probably not a good idea.
I want to point out that this exact yellow color has shown up in this video several times already, and in particular, all the times that glass is broken into plasma. This is because sodium in the glass is coloring the plasma.
Sure.
Now, Nile Red actually has an entire video on this very effect. It turns out, it only takes a little bit of sodium to make a lot of yellow light. And this can be a blessing or a curse depending on what you're trying to do. With yellow down, let's move on to green. I'm mixing up some trimethylborate, which will hopefully show off boron's spectral colors. Since this isn't conductive on its own, I'm using a sliver of aluminum wool to initiate it.
So boron, at least if back over in the fission world, is actually absorbs neutrons way better than uranium does when it's about to fission. So that's why it's used in control rods. Boric acid is also used as well for reactivity control. Just think of it as liquid control rods. Yeah, boron comes up quite a bit within the nuclear industry.
It's funny because the free boron must have been thousands of times more concentrated than sodium in there.
So the irony is, in the nuclear industry, you typically use it to shut down a glowy thing rather than causing the glowy thing.
Yet it's the sodium yellow that stuck out at first. Eventually, the boron won out though, making a nice green color. Well, green was easy enough, so how hard can blue be? I figured copper would be the element to zap, but then I remembered that when I melted it, it didn't make much blue light. But that's the thing about copper. It has to be tickled in just the right way before it'll spit out blue light. And this is why blue is such a challenge in fireworks. So, I tried a pyrotechnics trick and added a source of chlorine in the form of copper chloride.
Wow.
This one sucked. I was hoping for blue emission from hot molecular copper chloride, but this really only made a little bit of blue. Maybe the plasma was too hot and I don't know, let's try something else. Microplastics. Maybe this will provide a better form of chlorine for the copper. There were a few good flashes of blue in there, but still not what I wanted. Maybe I just need to change metals.
Battery, yeah, there we go. Chop up the battery.
I carefully opened up a lantern battery to extract the zinc metal casings.
Carefully.
And what do you know? Sodium yellow.
Yeah.
I even tried a strip of high purity zinc, and although this one briefly flashed blue, it was still the trace sodium contamination that stole the show. Yellow chemistry at its finest. Embarrassingly, the bluest plasma I've gotten so far was actually just the aluminum foil I zapped earlier. Out of desperation, I decided to try this again in a bigger beaker, with the hopes that the higher volume would lower plasma density and favor atomic emission.
And the reason why that's the case is it just lowering density just lowers the probability of collisions. And the excited ions just go back to their lower energy states. So a lot of what you see is caused by atomic emission, which is just when a photon's emitted from an ion going back to its lower energy state. In other words, just increasing the probability of blue glowy things to show up. That's cool. I think that did it.
Wow. All of those fancy chemicals and elements, only to be outperformed by a strip of aluminum foil. Chemistry is stupid. With blue finally down, it's time to take on indigo. And there's no better metal for indigo than indium. It's no coincidence they sound so similar, because indium was actually named after the color indigo. Why this is becomes very apparent when indium is zapped by my demon circuit, as it makes more indigo light than I've ever seen in my life.
Oh, that's beautiful.
Can the same be done with a macrowave? Let's plasmify some indium wire and find out. Blue? Ah! I tried so hard to get blue earlier, and now it shows up when I don't want it.
Ain't
Figures.
That truth.
Instead of indium wire, I melted some of the metal in the bottom of a beaker, hoping that it would provide more metal to the plasma. Nope, still blue. In hindsight, the ceramic fiber base was probably poisoning the color there, but I didn't consider that before trying the next experiment. I added some indium chloride, hoping either the chlorine or pre-ionized indium would change the color.
Let's see.
This was a big improvement, and although the plasma was a bit obscured by the smoke, I would have probably stopped here if it wasn't for the next
Looks pretty indigo to me.
experiment. As a side note, I should mention that while indium metal is essentially non-toxic, indium smoke is really bad to breathe in, as is ceramic fiber dust.
Generally, it's a bad idea to breathe in any ceramics, metals. That stuff's not really good to accumulate in your lungs. A lot of people know about how radioactive uranium is. People forget that if you were to huff uranium, you get about as much toxicity just from it being a heavy metal, the chemical toxicity, as well as the internal radiation dose. So uranium's kind of a twofer in that regard, but people seem to forget about the chemical toxicity too.
These are one of many reasons I'm wearing a respirator. Anyway, I decided to try macrowaving some gallium crystals. Most people know gallium for its very low melting temperature, but it turns out it has a beautiful emission spectrum as well. Some crystals in the bottom of a beaker were enough to give some interesting colors, and flipping the beaker over really brought out the color. And what do you know? There's the last of the colors, violet. I didn't stop there though. I was curious what would happen if I made an alloy of gallium and indium, and then zapped that. Sure enough, a nice clear indigo started to come through. After playing with ratios, and settling on an alloy that was mostly indium, I created my favorite plasma of this entire project.
Whoa. That is so cool.
Holy! Wow! Wow! That was perfect!
It was beautiful.
That was beautiful!
Looks like those artist renditions of nuclear fusion reactors that you see.
Yes! Yes! Ah, that was perfect! Oh, so beautiful! Ah, I'm sorry. I've made every color I wanted to, and melted every element I wanted to. And I don't even want to stop here. However, this video is getting pretty long. There's still so much more I want to do with my huge magnetron.
What is that?
I even made this cool Faraday helmet for some of my more cursed ideas. I should probably save
that in and of itself looks pretty cursed. Looks medieval.
Those experiments for a separate video, just because I don't want to rush through them.
Yeah, take your time.
Instead, let me try to address some questions that I just know you guys will ask about otherwise. What does it do to electronics? Well, most things I threw in there gave the same result. RAM sticks? Plasma.
Yeah.
Neon bulbs? Plasma. PCBs?
Ooh, wow.
Plasma. Christmas lights? Some funny colors, but mostly plasma.
I like the colors though. Yeah, he's using multicolor. That's good.
The only electronic device that didn't ionize was this broken calculator. But the smoke it made was essentially a chemical war crime.
Oh, wow.
I tried CDs as well, but their coatings vaporized in a fraction of a second.
That's cool though.
So, what about the health risks of this contraption? Well, the real risk here isn't microwaves, it's the power supply. Now, put simply, you touch any of this stuff while it's live, you'll die instantly. Yeah,
the power supply and the hazardous chemicals by what you put in there.
But as for the tiny bit of microwaves that escape the oven, those are harmless for the same reason your Wi-Fi router is harmless.
Yeah.
And that's because microwaves are non-ionizing radiation. Hold up.
The main hazard associated with one would be if you were somehow, like, within it to the point where it would heat you up, but it's not the radiation effects. The energy levels are too low. And that's because of the spectrum. As far as microwaves themselves and the radiation interacting with the body, it doesn't make a difference if it's 2,000 watts or 20,000 watts. That changes the amount of heat quite a bit. And like Styropyro said, a lot of the electrical components around it can be quite dangerous.
Microwaves are non-ionizing radiation? Didn't I just spend the entire video ionizing stuff with microwaves? Yes. So let me explain by briefly talking about radiation. Now this word scares a lot of people because they associate it with scary forms that cause cancer. But not all radiation is this way. Microwaves are a type of...
And even of the ones that do, you need to just get a high enough dose. It's order of magnitude just like anything else.
Electromagnetic radiation. This type of radiation includes scary stuff like X-rays, as well as just light. This does not include particle radiation, like you get from some kinds of radioactive decay. Now this is where things get confusing. Ionizing radiation includes high-energy EM stuff, as well as particle radiation.
So ionizing, about ultraviolet being ionizing, it's kind of in a transitional region, and I've seen the line drawn differently on different scales, so this is fine. UVA, the stuff that ages you, non-ionizing. UVB, the stuff that can cause sunburns and increase risk of skin cancer. I've seen it referred to as either non-ionizing or partially ionizing. And then UVC, which is mostly blocked by the Earth's atmosphere, that's fully ionizing.
And nuclear radiation falls here as well, but not all ionizing EM radiation is nuclear radiation.
Nuclear from EM is generally X-rays or gamma rays, nuclear referring to radiation that's emitted via radioactive decay.
If that makes sense. Okay, all that considered, you may have heard that light has properties of both a particle and a wave, right?
Mm-hmm.
Well, this is where the distinction of ionizing comes in. Ionizing EM radiation is where one light particle, or photon, has enough energy to strip an electron off of an atom and ionize it. Photons with this energy can mutate DNA, leading to cancer. I
just love the pile of old X-ray machines.
Microwave photon is literally 1,000,000 times weaker than this threshold.
Oh yeah, we're talking... And the ionizing threshold kind of moves a bit. It's on the order of tens of electron volts, and microwave is on the order of micro electron volts, so yeah, he's not exaggerating. And to pile on, we're talking in the tens of electron volts, just barely enough to do so. Not talking about, say, X-rays on the order of hundreds of thousands of electron volts or gamma rays on the order of millions of electron volts that do it really easily. Of course, they're higher up the spectrum of ionizing radiation.
Now, to be fair, a photon doesn't have to be quite at ionizing energy to be cancer-causing, as UV can still cause damaging photochemical reactions to DNA. But even this is 100,000...
And that's also where you get into the weirdness about UVB radiation being partially ionizing.
...times more energetic than microwaves. Then how do microwaves ionize stuff? So bear with me. I've already mentioned that microwaves are
intense electromagnetic fields.
Which means they have an associated electric and magnetic field. Now, it's the electric field that's relevant here, and an important property about these fields is that they add up. That means that when you put enough microwaves in a small enough space, the electric field grows to the point where it can rip apart atoms and molecules on its own. This effect is not exclusive to microwaves,
lasers.
And even visible light will ionize air if there's enough of it. Sticking your hand in the oven won't shoot a bunch of holes in your DNA and give you cancer. It will simply cook it like you dunked it in lava. Of course, burns only happen at huge powers. At low power, like what leaks through the oven door, those risks simply aren't there. Oh, and for the record, I did measure the microwave leakage from this, and it's so small that it's well within the legal safety limits of what's allowed to be sold for.
That's good. I'm glad he brought that up. So, yeah, microwaves aren't a hazard here. Now, having a transformer that you normally put on a telephone pole, yeah.
Home use. It's incredibly well sealed. Well, other than one mishap where the tape on the door exploded and EMP'd one of my cameras. But, we don't need to worry about that. So hopefully that convinced you that microwaves are safe in small amounts.
That's good. I'm glad he took the time to explain that sort of thing. And as far as his explanation of electromagnetic radiation, spot on. Thanks so much for all the recommendations for this video. And thanks so much for watching. I'll see you next time.